All right, so let's see. Let's see how can we wrap this up. What are we missing? What is missing in this picture now? Well, one thing that is missing is that the entire framework. How does the entire framework work? How does the entire framework is supposed to work? And again, I said this the first day. If you don't know machine learning, you don't gonna learn it now. But if you do know machine learning, then we have.
I think we have to.
I already did.
The recording?
Yes,
Oh, okay.
it's right. You see.
Read me.
The vocabulary we have is in common. So what does it mean to perform an experiment in every machine learning exercise? So in our machine learning exercise as well. Well, you start from the data and you pre-process it. Now, pre-process it can mean anything in the machine learning community. If you have a time series, like for example, in the last part, when Giovanni is going to show us how we did this, starting from a data that it was recording of voices, of cough samples from people who were diagnosed with COVID or diagnosed with not COVID, so no infection. So the original data was just a voice recording, MP4. But an MP4, it's a temporal series, a time series, only if you pre-process it. What does it mean to pre-process it? It means to extract all the frequencies, and those frequencies become attributes. So now you got, let's say, from 50 hertz to 300 hertz, and then on that you can apply our feature extraction function. So that would be the standard pre-processing. And then in our case, it means pre-processing means also or immediately after pre-process, you gotta decide what modal logic you want to use. And we said that before, and I gave you one example, but it could be many. Even within the interval temporal logic that we saw yesterday, which is the same one that we saw today, deciding the modal logic could mean, okay, don't look for later intervals, never, because for me it doesn't make sense a rule that says later interval, but do look for during intervals, because to me rules like that, if there are any, do make sense. So this is something that you have to decide at some point, and of course the set of functions. He said, in many cases we can just use max and min. But max and min are just useful because they are interpretable and because sometimes they do extract some usable information. But if you look, for example, at the literature of time series, there are like hundreds of functions that people have applied to all sorts of temporal data. There is even one pretty recent work, I don't know how many years ago, maybe 5 years ago, in which these people took all this dictionary of 100 functions to apply for, they could be applied to temporal data, and across completely different data sets that mean completely different things, ask the question, which functions are the most informative across all temporal data, and they come up with 22. I think you saw this name, Catch 22, somewhere in his Jupyter. No, they come up with 22 functions that look really informative, independently across different temporal data, whatever they mean. So what we did was we implemented all of them. Actually, they were just already implemented. We just included all of them. Remember, every function that you can apply to entire time series, you can apply to an interval. That's the whole idea. And now we have a very big dictionary of functions that you can use. So you apply. You apply feature extraction and selection. This is something we didn't talk about. We are going to do it now. But what does it mean? Well, again, voice means, apply Fourier, for example, to voice samples means getting up with, I don't know how many variables, 10, maybe 20 different frequencies. And then you got 20 functions, which means there are 400 attributes. 400 attributes over, let's say, 50 or 100 points, which means 100 points means around 10,000 intervals. That's already too much, okay? So we're gonna look into what it means to do feature extraction and selection. So feature extraction is what I just said. Selection, how do we select them? How do we choose which one are more important? This is a very well-known concept in in general, in learning, independently of the methods. What we did was just, take those ideas and make them real here. We didn't invent almost anything here. Apply the transformer. We already know what that means, and then learn. But is it learn enough? No, because then what he just did for an hour was evaluating the model, maybe post-hoc treating them. What is post-hoc treatment? Well, say, for example, take a rule and convert it into English, or take a rule and modify it just a little bit and see what happens. And each one of these steps can make us go back to a very early step if maybe it's necessary. Maybe we just have to learn again, or we have to change completely the logic, maybe modify the logic or the set of functions, or maybe everything was right, but we didn't just we just didn't select the right ones. Okay, so that would be a very high level schema of a complete experiment, which is something that we do many times. So now let's talk about feature selections, and then evaluation and post-hoc treatment of the model. So what does it mean to extract and select symbolically? Well, you said you have experience with learning, and so I'm wondering, did you ever perform a selection exercise? Did you ever perform a feature selection exercise sometimes? Possibly? In the classical case? Did you? Did you ever look into the variables before learning and said, I want to use this instead of that? No?
For my application, no.
Why?
I just use the straight values. I'm trying to...
You were the one looking into physical values, right? So from your point of view, your data were already clean enough somehow that you can... But... Actually, you can't say that because maybe it does make sense to you. It does make sense to you before learning, but then by the end of the process, you may realize that some of the variables were never used during that. If you can look into the model, but again, your data probably have just a bunch of columns, just a few of them, right? You mentioned only a few variables, only a few attributes, right? So. That's probably the idea. What about you? Did you? No, you don't know. You weren't here the other day, but do you have an experience in learning before?
A little.
All right. So have you ever done a feature selection exercise? Classical feature selection exercise. Say this variable yes and this variable no, via some statistical method.
It's extraction or selection.
It's the same, selection. Okay, so did you do it?
Yeah, I have done.
Okay, and which method that you used, if you can remember them?
I don't remember.
You don't remember. All right, then. So feature selection tabular data, which is classical data, not the one we're talking here, non-tabular data, but starting from tabular data, is the process of selecting a subset of variables, say this variable yes, this variable no, with the aim, well, if you look at the original definition, it says, with the aim of reducing the amount of data is the learning process, and stop. And then I add into this, gain initial information on the problem at hand, okay? So a common misconception about selection is that selection is only useful for computational reason, but that's wrong. Even if I had unlimited computational power, I would like to select anyway because the selection itself tells me something about the data. Stepping up to the model case, the process can be generalized a little bit. That is what it is about and what we're talking here. And we can ask the question not only of which variables, but also which functions. As I said before, I say there are many functions that I can apply. How do I choose which one is better and which one is worse? So, well, actually here there is a typo here, but which variable in which function means which attributes, and which words contains the most information for the problem at hand. Let's take the example that we already said. You know, the gestures that we should be able to distinguish whether or not this guy is telling the plane to come or to stop. It makes sense to think that possibly right at the beginning of the gesture there is no information. Okay, because he always starts like this, and then he starts moving, and there is a little initial interval of time in which whatever he does, it doesn't help me distinguishing between the classes. It makes sense, right? I mean, it makes sense that at the beginning of the gesture, at the end of the recording, but whatever it does, it's not really informative, no? How can we do this? Automatically is the question. How can we do this in a systematic way? If you don't know feature selection, you don't know the classical division, the classical classification. Again, pun intended here. Between different ways of selecting. But classically, if you speak to any machine learning practitioner, he would say, or she would say, you can select using filters, you can select using wrappers, you can select using an embedded method. Now, what's the difference? Usually, with filters, we mean select before learning. And apply any statistical method, and that is exactly what we have to discuss here. Apply statistical methods that have nothing to do with learning, with the learning phase, and choose whether or not you want to include that variable. Wrappers means, okay, I don't want to decide beforehand. I do want to know whether or not my method works better if I throw this one in or if I take it out. This is a wrapper method that works in combination. So first, the result of filters is independent of the learning method, while the result of a wrapper depends on the learning method, of course, because every learning method is an approximation. It means that its behavior is non-linear. It means that it doesn't matter. You cannot predict whether or not it will work better if you add variable A, B, C, and then you want to add variable B. There is no way to predict the corresponding behavior if you start eliminating one of them or another one. It's completely non-linear. Therefore, the wrapper method do make sense. Usually, wrapper method works like this. Just throw a bunch of random selection, evaluate what the learner did, and then modify your selection. It could be completely random, just try 100 combination. It could be, I don't know, genetically guided with a genetic algorithm that says modify the selection and in this way to maintain local optima or whatever. But the difference between these two is that the result of the selection depends on the specific method, on the specific learning method. What's the consequence of this? Well, one easy consequence of this is that, okay, look, if I have to use a wrapper, then computationally speaking, whatever time I spend for one learning exercise, I get a multiplier for how many different selections I want to try, right? So because these selections are independent of each other and the behavior is non-linear, it means that basically there is no other way than multiply the two computational efforts that I have to do. Therefore, if your learning method is already computationally heavy, then selecting by wrapping is going to be exponentially heavier, right? What is an embedded selection method? Embedded selection method is something that, we should define it a little better, but it basically means that your learning method also does some kind of selection during the method itself. So it means that if I have a learning method and then I want to convert it into an embedded selection and learning method, I got to change the method. Therefore, using embedded method means rebuilding from scratch, or almost from scratch, your learning method. Now, we just spent a very long amount of time to invent a new method for learning. I'm now going to scratch it down, and I'm now going to throw it away and start all over again. So let's say we don't want to do embedded methods just yet. Also, wrappers, we said it's computationally very heavy in general, even with existing ones and even with easy ones. I mean, my experience in wrapper are typically with classical decision tree and genetic algorithms, and it already takes weeks of computation in order to get a good selection by combining a classical decision tree and the genetic algorithm. So those are also out of question right now. So let's focus on filters. And filters, and of course, this order here is not just a computational and informationally wise. These are not just computationally, informationally wise ordered from top to bottom, but it is also true that probably the result of filters is less reliable than a result of the wrapper of an embedded somehow. I'm speaking out of experience here. There is no mathematical definition of what I mean. Usually filters work a little worse than the other method. There is some mathematical content in this sentence anyway. Filters are usually univariate, not always, but typically they judge one variable at the time. You can do filters in the multivariate context, but typically filters judge one, take a decision on one, maybe compared to the other, but not in the sense of a group. They don't give you a group. They give you a decision for a single column. I'm in the non-modal case now, just to have our vocabulary, our dictionary right. Okay, so we're gonna focus on filters because they're easy to implement. They're computationally more feasible, and we're gonna close our nose and hope that univariate reasoning is enough for us. Okay, so two steps can be identified at dimension 0 for filters. Filters usually work in two different ways. I call them steps. While in the classical literature you could find this just two different ways of selecting something. I call them steps because in our case what we did was put them together, so we got one idea of selection, and you can stop at the unsupervised step or go through to the supervised step, or skip the unsupervised step altogether and go to the supervised one. Remember, we are focusing on supervised learning, so I am assuming my data is labeled, and then I can still do some unsupervised selection by ignoring the data. We're not I want you guys to be very, very, very clear of the numbers we have here. We're not selecting among 10 variables. We are selecting among thousands of variables here. Now, it's easy to see why. Because if there are tens of variables to begin with and tens of functions to apply, and then again, all of this may make sense on some world, but not on other worlds. So it means that we are already in the thousands, okay? And now selecting in the thousands could already be difficult enough at the filter level. So if I can get rid of something at the unsupervised in an unsupervised step, well, much better for me. If there is a way to do this, then much better for me. And before going to the supervisor, of course, I said selection and extraction and selection must not be only related to learning. So it may be the case that my data is not labeled, and yet I can still do some unsupervised selection and get some information modally. Why do I say modally? Because what we can do is step from the dimension zero case to the higher dimension case. Okay, to the higher dimension case, which is, as we said, a very typical application of model learning. So how do we generalize this? In the unsupervised step, we select variables, feature extraction functions, and or worlds with methods that are independent from the class. And then, for the ones that survive the first step, we select the triples that using the class information. I didn't say how yet. I didn't say how, and I didn't say how this is related to the original one. Well, so what happens in the original case? In the original case, you have your column. Sorry, the original. I mean, in the propositional case, you got your columns. All right. So a typical unsupervised selection here is, hey, tell me whether or not there is enough variance. Why? Well, for example, zero variance columns means no information. It doesn't matter what you want to learn from that. But if the data never varies, it means there cannot be information. Suppose that instances are labeled 0 and 1. Some are 0, some are 1, but column A doesn't change, never. It doesn't matter if I can't relate it to the class. I know there is no class information there, so I can just throw it away. So that would be what happens at dimension 0. How do I do this in the model case? Well, what I can do is, okay, this is how my data look like. Again, I'm sticking to the temporal case because it's easier to understand. So we start from the concrete representation of a data set of dimensional case, dimension 1. Remember, this is my blood pressure that changes over time. This is my pain level that changes over time, or whatever. And what I do is consider my set of features. Hey, I want to do maximum, minimum, and number of variations. So for example, I apply each one of them to each interval of each instance. So I am splitting this information of all the worlds, and I get a bunch of new variables. This is not where we're learning from. This is just to judge them, all right? And now remember, I gotta be able to judge them and then go back to my data having selected something, all right? So this is a temporary representation of my data. So what is this, for example? It could be the maximum in this interval of this variable. And this one is the minimum of this other variable in this other interval, and so on. But now I can apply the old method. Now everything has been flattened down somehow to it's propositional again. Now hold on this thought for a moment. This data is propositional. Let's keep this idea in our mind, and we go back to it for 1 second. In 1 second. But right now, just think of this as just a bunch of numbers. Well, now what I can say, assuming that I'm filtering in a univariate way, let's take it and judge its variance. Zero variance. We'll throw it away. Wait a moment. What do you mean you throw it away? I can't throw it away. I cannot throw it away the interval 1, 2 just for this function and just for this variable. So this is not how we can do it, right? What I can do is order them by variance. Or that I can. So how would I don't have the pictures here, but just think of it. How would look the result? Well, I could order them, and then let's say I normalize somehow the variance. Let's say I use standard deviation instead of variance, because so it is in the same unit of measure. Or I just normalize them all so that I can compare them, and I put them in a graphic. And it says on the y I have this measure of variance or whatever it is, for as long as it is comparable, for as long as all of them are comparable to each other. And then on the x, I've got all of these triples enumerated somehow. On the left part, the one that varies the most. On the right part, the one that varies the least. Right? Good. Let's say I want to do only unsupervised, okay, step. I'm forgetting about the class now. Yet the problem already arises. How do I select them? Well, of course, I want to keep the one on the right, the one on the left of my grid, and then throw away the one on the right. So if I do something like that, I end up with very scattered information. It's information that I cannot parse, because each one of the triple talks about specific intervals, specific function, and specific variable. I cannot use it as I cannot just throw it away, because I cannot go back to my original data if I do like this. But what I can do is that, okay, let's group together everything that survived, the triple that survived, and then let's apply a further statistics on that. Say, let's see what intervals or what function occurs the most in the group that have survived, or what function occurs the least in the group that have survived, and throw them away from the function vocabulary. Then let's see what original variable occurs the least in the group that have survived. In general, I can say that variable is not very informative. Let's throw it away. And now this is called, you can see, now we have 3 dimensions here. Worlds, functions, and original variables. Let's group the surviving result in each one of them in the order we want to, and different orders will give us different results. And each grouping will give me a method to arbitrarily decide that I can take one piece of my original information and just throw it away. So indirectly, I'm using the classical statistical method. I don't have to invent anything. As a matter of fact, our selection package does have a dictionary of classical function to apply to zero-dimensional data. You get your own one. Just throw it in the mix, no problem. Use any one you want, because now what we did was convert the modal data temporarily to tabular data, apply the method, and now I have a way back from this. All right. You should say I could also do this for worlds. I just group them away. So what world occurs the least in my informative schema? I can't just say then throw it away. I can do it, but only on certain conditions, because I gotta be able to go back to a full Kripke structure that has the properties. So If it were the case, like I said before, that at the beginning of my movement there is never information, well then that part of the model I could throw away because it's easy. Let's say the first 3 points of the time series never contain information, and every time series starts at point 4. That I can do. But if it came up that the interval 714 doesn't have information, is not as easy to just throw it away. We didn't work out this case. So right now in our FS package, you can group them, but not by words. You can group them by words, but you cannot actually eliminate words. So what it is useful for? Well, okay, it already gives us some information. Usually our package gives us the result in a group of pictures, very informative pictures that tell you which function, which words, which variable contains the most information, and it does some bunch of statistics on it, and it's already a result on its own, as a matter of fact. No? So we select the set of triples, then we aggregate them in order to interpret the result, and then we go back to, let's say, I decided, oh, look, V2 never occurs on the informative ones, and so, sorry, V1, so I'll just throw it away. So variables found to carry too few information can be excluded. Function to extract, found to extract too few information can be excluded from the learning process. To ensure completeness of the model, the intervals are kept in any case, but yet you got the information. And there probably is a way to, let's say, prune somehow, cut a little bit from the Kripke structure, which we didn't think about this for long enough to tell you this is the way yet. Okay, so the information gained during the process is still relevant on its own. It can be validated with standard statistical univariate method and techniques. Of course, I just gave you the example on the unsupervised, but then you understand the supervised is exactly the same. Okay. Usually, in the two-step, in the complete process, we got the 2 steps, and we do like this. First, throw away the second half variance wise, and then so from 10,000 now we got 5,000 triples. And then from that, apply a supervised judging method to order them by some kind of metrics that allows us to compare a triple with another triple, and order them, and then give me just the first 10%, and now tell me, in the remaining 90%, group them together, tell me which function occurs to the list, which variable occurs to the list, throw it away from the original data, and you got the smaller, data. That is what you wanted at the beginning. So for higher dimension, you can generalize this by simply using hyperwindows instead of intervals. Of course, throwing it away, judging hyperintervals is not as intuitive as judging intervals, but it can be done. And well, for other types of unstructured data that is not dimensional, like text or graphs, we just didn't think about it yet. So we don't know how we can do it. Of course, there must be a way to do it, but we just didn't think about it yet. So now we got almost all the pieces together. Yeah? We know how to treat data, to build formulas, to build simple models like decision trees. We know how to treat our data so that it doesn't look too big. And let's just put this on in the mix. If you have experience with learning specifically in the subsymbolic realm, then you know that computation is an issue. And usually, for example, say for neural networks, it is a GPU type of computation, right? So In the symbolic case, it's a CPU type of computation, okay? So if you want to do this, you need a specialized server. Like, for example, we have one. We build it on our own, and in such a way that it's optimized for this kind of learning. Now we got, I said, we got almost all the pieces. What are we missing now? Well, one thing that he was been mentioning, and then Sasha has asked about, is how do we evaluate things? But this is not a new concept. This is the old one. So there is nothing new here. Models are subject to the same evaluation as any other one. So in our system, you will find exactly the same terminology. And in 2 minutes, what I want to do is just remind you of this terminology. But let's focus on classification problems. Classical concept, how do you statistically evaluate a classification model? And basically, it all boils down to the question, on which instances is the learned model tested? So that's the basic question. If you test it on the same one that it has been learned from, then it's called full training evaluation model, and it's usually useless. Or it is useful if the result is really bad. So if the result is bad in full training, you just throw everything away. Something was wrong to begin with. One of the steps was wrong to begin with because you weren't able to even to overfit. So something was wrong in the process. If the data set is used partly for learning and partly for testing, then we call this training plus test or training and test evaluation model. It is partially reliable. Why it's only partially reliable? Because it depends on how lucky you were when extracting the test, right? Sometimes it's the only thing you can do. It also has some added value. Sometimes we overlook on this. This is the added value. The typical, if the training practice is the typical way in which you compare yourself to others. Because if you download open data, the data that others have used, if they done the job right, they will give you the instance and the test. Sorry, the training and the test. There is nothing special to it, except the fact that everyone knows what to learn from and what to test for, so that every result can be compared to each other, right? So this is something that we should think about. But in general, if your exercise is your own exercise, then the most reliable way is cross-validation or n-fold cross-validation, as you called it. So in the data set is sliced in several subs, and each one of them has played in different models the learning, the training and the test role in a systematic way. And then how do you evaluate? You average the results. So this is the most of. I'm not saying anything new. Maybe you had experience with learning, but you didn't have experience with learning in the real industry. And when you really have to go to the end of the exercise and give the model that works. Now, if you gotta do that, you got to think about how to combine all this together. And so how do you combine this together? Well, as I say, you evaluate it in full training usually to see whether or not we are going in the right direction. Then you do several combinations of the testing mode to adjust your parameters, work with the models, blah, 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 blah. And then what do you do? What do you give back to whoever asked it? You give back the full training mode. Why? Because it's the most reliable one. So you judged the way to do it by testing in all these ways. But then when you found out that the language is that one, the proposition are those, these are the parameters, blah, 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 the last step is exactly the first one. So take the full train mode, and this is the one you give back. Why? Because it is the one that has been trained on the most instances, and therefore is the most reliable one. It wasn't reliable to begin with because you might have possibly overfit or whatever. But once you have decided the correct parameter, you know that it won't overfit, That is exactly the purpose of the exercise. It didn't overfit, it is reliable, let's train it again on the all instances that you have at your disposition, so you give it back to whoever asked. And by the way, we sometimes do this part, sometimes we do it in this way, sometimes we do it in another way, which is the one you were seeing before. We don't, in general, we don't need to give back a black box. Now we know how the model is, so to my guy, I can just say, look, you gotta look for the minimum in this interval, and that's the only thing that makes a difference. I don't have to do anything else, right? Only sometimes it's not that easy. Sometimes the information is just complex, so it is convenient to give back a tree, a forest, or whatever. But in general, symbolic learning means learning the theory of the phenomena. Once you've learned the theory of the phenomena, you can just translate into natural language if it is formal enough, if it is precise enough, or in the logical language. It does not have to be this logical language. It can be anyone, for as long as it is for as long as it is precise, and that's what you had to do. For each one of these method, what do you measure? Well, if it is a classification problem, you measure your error. If it is a regression problem, you measure your distance in somehow. If it is unsupervised problem, you gotta find a way to extract the statistical indicator of how good is your model. We're not going into these details, but there is something that can be said here, which methods are better than the other, and so on. What is the error in the classification model? Well, basically everything boils down to a confusion metric. Confusion metric here is shown in the binary case. Usually you can do it in the multi-class way, and you just judge your true positive, your false negative, your false positive, and your true negative. I think I'm using some terminology that you all know, so I don't want to go into this definition, but whatever indicator of your error you want, you can extract it from here. Just combine these four numbers in a different way, all right? So there is tons of literature in this, and that ask you, that teach you how to judge the error. So you have to combine the testing way with the measure or the measures you wanna take into account, and this is your evaluation. So TP, TN, TP, FP, and FN are combined into several metrics that give you several indications of performance, and so basically this is how the exercise will look like. I promised you on day one that we are able to learn from different sources at the same time, and these sources can even be completely different from each other. Typical example, time series plus an image. Another typical example could be, I don't know, time series plus its propositional version. If you remember, 10 minutes ago, I said that this looks like a tabular data. So somebody, I know I did, somebody could come up with a very simple idea and says, look, since you spread your information on all your words, all your function, all your variables, why don't you just stop there and learn a propositional decision tree if you want to? And then I say, okay, what happens if you do? Well, what happens if you do is that I'm not judging if it is better or worse. What I want to argue here is that it is different. It is different from learning the model, its model version, even if the information is the same, because what you can think, what you can wrongly think of, the wrong idea here could be, look, everything you did was to interpret your model via a transformer. Then once the transformer is applied, the information is already there. You don't have to invent a new method to learn. In fact, we did. Why? because learning that this happens, let's say you learn some kind of hard constraints on this column, the column talks about a specific interval which has a name. And I said day one that modal logic is qualitative, not quantitative. It doesn't talk about the name of the world. It talks about how the words are related to each other. So it may very well be that your class is distinguished by something that happens on the interval 1, 2. If that is the case, then this one is a good way to learn it. But if it happens that the class is distinguished by the existence of some interval where something about this interval is qualitative related to some other one, but it doesn't have the same name in all instances, because sometimes it's longer, sometimes it's shorter, sometimes it's little displaced on the right, sometimes it's little displaced on the left, then here you can't learn anything, while modally you can. Since there is no way to judge to begin with, there is no way at the beginning to judge whether or not this is the case or the other one is the case, well, in general, you should try both. Now, we go back to our multi-mode learning, because learning from different sources could also mean learning from the propositional information at the same time as from the model information. So the propositional frame is just any other frame. Now, let's go back to our COVID exercise, which we didn't yet, or the gesture exercise. It could be the case, as we said before, that everything that counts is what happens at the interval named 1, 6. If that is the case, then propositionally speaking, there is enough information for you to learn. It also may be very well the case that some class depends on the interval 1, 6, and some other class depends on the fact that one gesture is during another one, or the thumb being turned towards the ground happens during the arm raising. But if you do the other way around, say for example with the static one, it doesn't mean anything. It may very well happen like that, right? So what if one class is decided by the first kind of information and the other class is decided? We don't know that. So either you learn in 2 different steps and you may be lucky, or you multi-mode learn. If you multi-mode learn, if I didn't say how we do it, now I will tell you in a second. I will say, but this is easy, and it is easy. In fact, it is easy. But just think about of this in abstractly. If you could do it at the same time, then you don't have to decide, right? So how is this done? This is another example. The patient described by more than one diagnostic exam, the EEG plus CT scan. So the example is okay. So this particular condition is that sometimes depends on the fact that the EEG on this particular electrode goes like this, and some other time you can see it better on the CT scan. How do we do this? Well, first of all, this method is not specific of modal learning, but it can only be applied during modal learning. Why? Because modal learning gives you different representation of the data. Now, if you don't have modal learning, then you have only one representation, and therefore, even if the method in principle can be applied, it doesn't mean anything. So, can a single algorithm like CART learn from more than one source at the same time? How will we do that? Well, remember how the method. What's the basic principle? Local optimization. I'm in a node of the tree now, and I decided I want to decide whether the split is better with P versus not P, or Q versus not Q. This is the basic, right? In our case, it would be also diamond true versus box false. Doesn't matter. Local optimization. What if I take the two frames at the same time, and in a single decision, I decide whether or not it's locally optimal to distinguish between P and non-P on frame 1 or Q and not Q on frame 2. If I can measure, if the amount of information is always comparable, then it's just yet another dimension on which we decide. Model decision tree have shown the ability of learning from unstructured data, and therefore what you can do, say you want to learn from these two at the same time, what you can do is that your first split goes here because you optimize this. You try the first split with every possible phi 1 and negation of phi 1 on the time frame, as well as every possible phi 1 and negation of phi 1 on frame 2. You can do this. And your local optimization just gave you another information. It says, look, it is better to split on time frame before the splitting on spatial frame. And then it's all over again. We are saying your instance is here. And now let's try local optimization again. Try all the possible way to split on the time frame and all the possible way to split on the spatial frame, and so on and so forth. So now we are what we end up with is a model decision tree that looks like exactly as it would look before, only formula have been labeled with the frame on which they should be interpreted. Which means that when we learn, when he's going to tell you, okay, let's look at the formulas now. So you know what you have to do. You go back to your on top. You climb up your branch, and then every time the frame says T, you form one formula, and then every time the frame is S, you form a different formula, and therefore the branch corresponds to two formulas, which you should check at the same time. Doesn't matter. You can always do that in order to decide whether or not one is one class or the other. So multi-mode or multi-modal, remember there is a difference between modality and mode of learning. Learn from multi-modal instances. Here the word multi-modal does not refer to the fact that the logic itself is multi-modal. It refers to the fact that you can learn from different modes. So each single mode in which the instance is presented is described in general with the multi-modal logic itself. For example, here we would be learning on the time frame side with interval logic, and on the spatial frame with spatial logic, which is the two-dimensional version of the time one. Okay, they look similar, but they are two different logic. Well, let's say here I want to learn with point-based logic, and here I want to learn with the spatial logic. If I want, I can do that, or the other way around. Okay, it doesn't matter. Or one of these two, or three, or four, or how many you want to, could be the propositional one. In that case, if you learn it with propositional logic, just as you did all your life. So the learning algorithm can be adapted to optimize greedily also the mode from which we perform a single split. And therefore, now what we're doing, we are boosting our technique. We started from a very hard and difficult one single model decision tree, which is, yeah, it got all the nice properties, but it's so hard to learn it in practice. And now we're decorating the whole process. Okay, now we know how to treat data to make it easier to first we take it, then we apply the transformer, then we select all the variables only the variables that make sense, only the function that makes sense. Maybe we also have a kind of information on the words that make sense, and we don't know how to use that, but yet we have it. Then you apply your modeling, one of the classical way, full training plus test, or cross validation. And if your data is multi-mode, you can do it. On what you're left with is, okay, let's do this seriously. If you want to do it seriously, usually you go with ensembles of models, only because statistically we know it's better. By the way, even in the neural network era, even when everyone talks about neural, somebody says, and it's not me, and I promise you, I mean, there are people that have been studying. So let's see, okay, is it really better to learn symbolically than it is to learn, say, for example, with ensemble of trees? And the answer is, they're pretty much the same. And in many cases, I'm talking here, I'm talking classical, propositional, random forests behave better. That's how it is, okay? There is a theorem, you can go, is it here, right? You can go to see this not very well known results that says a random forest can go up to the accuracy as much as you want for as long as you add more trees. It's a statistical glitch, if you want to, statistical loophole, if you wanna delete it. But just add enough trees, and you can boost your accuracy as much as you want. All right? Yeah.
As long as the variables that you have are informative, because
yes, of course. If everything is below 50% or 50%, then it doesn't happen.
I mean, if you start with an image, I mean, neural networks can be really good with images, and so if you want to apply a propositional random forest, you should transform it to a tabular version of it.
Yeah. And probably you lose information there. Yeah, you're right. But it's as you said, it's a loophole that is completely absurd. It doesn't say anything about images or whatever. It just says that ensembles can be really performant. So we just included it into the package. You can ensemble everything you want. That doesn't have to be the same one. Only if you ensemble purely symbolic methods, then you come up with a very interesting logical problem, that is, explain this logically, give me the logical corresponding rule that is challenging, but is also interesting because you feel you can do it. You just don't know how to do it, but you feel that all the information is there. So just think about it. And probably we can come up with a very good idea of how the model looks like. Of course, if you know random forest, for example, you know that somebody calls it a symbolic, somebody calls it a functional method because there is a function step. There's, for example, decision by majority. So how do you describe this logically? Well, there is a way to do it. We probably didn't find it yet, but there is a way. There is a way to do it. Now we have every element we need, and we can finally conclude by seeing this at work in a complete way.